Hello friends, here is a question worth sitting with. What do a ball flying through the air, a company's cost curve, and a roller coaster shape all have in common? They can all be described precisely by a polynomial. Before we define what a polynomial is, I want you to see why it matters. The height of a ball you throw upward follows a rule like -5 times t squared, plus 20 times t, plus 1. A company modeling its production costs might use something like 2 times x squared, plus 3 times x, plus 50. These are not coincidences. Polynomials are the foundational language of change, shape, and prediction in mathematics. And in this video, we are going to trace exactly why they sit at the heart of calculus. Let's start by pinning down what a polynomial actually is. Alright, let's lock in the definition. A polynomial is a sum of terms, where each term is a coefficient, multiplied by a variable raised to a non-negative integer exponent. Take the example f of x equals 4x cubed plus 3x squared minus 2x plus 7. Each piece has a job. The degree is the highest exponent present. Here it is 3. The leading coefficient is the number attached to that highest degree term, which is 4. The constant term, 7, is just a number with no variable. And standard form means we always write terms from highest degree down to lowest. Two key rules. Exponents must be whole numbers, and they cannot be negative. So something like x to the power of -1, or x to the power of 1/2, is not a polynomial. With that definition solid, let's look at how degree controls the shape of the graph. Now let's connect degree to visual behavior. A degree 0 polynomial like y equals 3 is just a flat horizontal line. One turn is impossible, with no variable at all. A degree 1 polynomial like y equals 2x plus 1 is a straight diagonal line, still no turns. A degree 2 polynomial like y equals x squared minus 1 is a parabola, curving up with exactly one turning point at its vertex. And a degree 3 polynomial like y equals x cubed minus 3x has two turns. It climbs, dips, then climbs again, crossing the x-axis at roughly -1.73, 0, and 1.73. Here is the key insight. The maximum number of turns a polynomial can have is always one less than its degree. Degree 3 gives at most 2 turns. Degree 4 gives at most 3. This pattern is not arbitrary. It comes directly from calculus, which we will reach in just a moment. First, let's see how we work with polynomials algebraically. Let me show you how we actually work with polynomials. First, evaluation. Take f of x equals 4x cubed plus 3x squared minus 2x plus 7 and plug in x equals 2. We substitute everywhere. 4 times 2 cubed plus 3 times 2 squared minus 2 times 2 plus 7. That gives us 4 times 8 plus 3 times 4 minus 4 plus 7, which simplifies to 32 plus 12 minus 4 plus 7. The result is 47. Now for addition. If f of x equals 2x squared plus 3x plus 5 and g of x equals x squared minus x plus 2, then f plus g just combines like terms. The x squared terms give 3x squared. The x terms give 2x. The constants give 7. The result is 3x squared plus 2x plus 7. Clean and systematic. Subtraction works the same way by distributing the negative first. Now here is where everything becomes powerful. Let's bring calculus into the picture. Here is the interesting part. Calculus uses polynomials constantly, and the power rule makes differentiation almost effortless. The rule says that for any term a times x to the power of n, the derivative is a times n times x to the power of n minus 1. Apply it term by term to our polynomial f of x equals 4x cubed plus 3x squared minus 2x plus 7. The term 4x cubed becomes 12x squared. The term 3x squared becomes 6x. The term -2x becomes -2. And the constant 7 becomes 0. It vanishes. So f prime of x equals 12x squared plus 6x minus 2. That derivative tells you the slope of the curve at any x. At x equals 1, the slope is 12 times 1 squared plus 6 times 1 minus 2, which equals 16. That is the rate of change. At that exact point, one consistent polynomial, carrying through from definition all the way to calculus. Alright, let's pull the whole picture together. We opened with real examples, projectile arcs and cost curves, to show polynomials are not abstract. Then we define them precisely, as sums of terms with non-negative integer exponents, written in standard form with a clear degree and leading coefficient. We saw how degree controls shape. Degree 2 gives 1 turn, degree 3 gives at most 2, and that maximum of degree -1 is not a coincidence. We operated on polynomials by evaluating at a point and combining like terms. And then we differentiated using the power rule, turning f of x equals 4x cubed plus 3x squared minus 2x plus 7 into f prime of x equals 12x squared plus 6x minus 2 in seconds. The key takeaway is simple. Polynomials are the entry point to calculus because they are easy to differentiate and integrate precisely. The natural next step is integration. We will get there soon. Thanks for watching, friends.